Section 1.5 Transformations of Functions. So to begin, we're going to talk about all the ways a function can move from a parent function. So a brief introduction would be if I had some type of, say, for a parabola. If I have just y equals x squared, that would be referred to as like your parent function. Well, with the parabola, we can do so many things. We can move it left, right, up, or down. We can also make it skinnier, wider. We can also make it open down. You can do so many things to change it from the basic or the parent function. So there are tricks, I guess you can say, to where you can know straight from the beginning what kind of transformations you have without having to graph it. That's what this section's about. Horizontal and vertical shifts. We will learn how to apply and recognize horizontal and vertical shifts. If a positive real number k is added to the outputs of a function y equals f of x, the graph of the new function y equals f of x plus k is the graph of f shifted vertically. Similarly, if I have a function y equals f of x minus k, then it's shifted vertically down. So if you have your function and somewhere on the side you are adding or subtracting a number, you're experiencing a vertical shift. Such as this example, we have a graph, we have the function y equals the square root of x, and we're going to take each point, and to our y, we're going to subtract 2. That is a shift down 2 units. So in order to write this in our equation, we would see this as y is equal to the square root of x minus 2. Notice that minus 2 isn't inside the radical. It's just, I like to say it's just hanging out on the side. So in summary, if I have a plus k on the outside, it's going to shift up. If I have a minus k, where k is any number, then it shifts down. Okay, horizontal shifts. If the argument of x of a function f is replaced by x minus h, the graph of the new function y equals f of x minus h is a graph of f shifted horizontally right. If the argument of x of a function is replaced by x plus h, the graph of the new function y equals f of x plus h is a graph shifted horizontally left. Still very similar. What's different is your adding and subtraction of a number is within your function. It's inside of parentheses, inside your radical, is inside. It's enclosed. Now, because of a number line, since from 0 to the right we have positives, to the left we have negatives, you might think minus might give you a shift left, but it gives you a shift right. If I have a shift with a plus, then we shift left. So take this absolute value function. My equation is y equals the absolute value of x. If I shift 2 units left, I take every x value and I subtract it 2. I move it to the left. The way this would be represented in our function would be y is equal to the absolute value of x plus 2. Even though we're moving left, recall by your definition, in your function, you're going to subtract to illustrate going to add to shift a horizontal shift. Graphing functions using reflections. Another transformation that can be applied to a function is a reflection over the x or y axis. A vertical reflection reflects the graph vertically across the x-axis, while a horizontal reflection reflects the graph horizontally over the x-axis. So here we see if we have an original function, which it's in blue, right? I can go ahead and reflect that down, which is illustrated here, or reflect across. Let's read the definition. Given a function f of x, a new function g of x is equal to negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about the x-axis. Given a reflection f of x, a new function g of x equals f of negative x is a horizontal reflection of the function, and it's sometimes called a reflection about the y-axis. Now, more commonly, I think we'll see a vertical reflection, but horizontal reflections also happen. Now, this is just taking our points and changing them over. To help you relate it to points, let's take a look at this example. A function f of x is given on the table, so this is our function f of x. Create the table of the functions below. So our new function, this is our new function, g of x, is made up by negative f of x. Now we have our x's and we have our f of x's, which are like our y's. So this is saying that what's different is that our y's will be negative. So let's create a chart for our function g of x. Our chart for g of x will be like f of x, but my output would be multiplied by a negative. So on the top, I have the same x's, 2, 4, 6, 8. On the bottom, I want the negative, since the f of x is your output, your y. So that'd be negative 1, 3, negative 3, negative 7, negative 11. And that is our answer. Now for the next one, I have a new function, h of x, and it's going to be made up by the negative x for every f of x. So this is telling me that let x be a negative, or multiply it by a negative. So our new chart would be for our new function h of x. It would be x and your output h of x. And let's take those four numbers that we have in our chart for h of x. I'm sorry, f of x. But let's take our x's and multiply them by a negative. So that I have negative 2, negative 4, negative 6, and negative 8. And my output will be the same. So that I have 1, 3, 7, 11. Even and odd functions. Sometimes functions exhibit symmetry so that reflections result in the original graph. Even and odd functions. A function is called an even function if for every output of x, f of x equals f of negative x. So this is saying if you plug in a negative, x, your answer is the same equation. If that happens, we say our function is even. 2. A function is called an odd function if for every input of x, f of x equals negative f of negative x. So let's say you plug in a negative and your answer is the same, but with a negative. Okay, let's take a look at an example. Is a function f of x equals x cubed plus 2x even, odd, or neither? Well, what's nice for us is that it takes the same step for all of them. For all of these, we are just going to plug in an x, a negative x. And our answer will let us know what we're looking for. Are we looking for, well, do we end up with the same exact equation or the same exact equation with a negative factored in the beginning, or none? It could be neither as well. Okay, let's go ahead and work this out. Let's plug in a negative x so that I have negative x cubed plus 2 times negative x. Okay, to begin, negative x cubed, well, negative x times negative x times negative x gives us negative x cubed. And then we have 2 times negative x, that gives us negative 2x. Okay, so we worked it out. Is it the same? And we compare it to our function and it's not the same. Okay, so because it's not the same, we know it's not even. Okay, let's factor out a negative. Let's divide everything by negative. So that I have negative, and inside I'll have x cubed plus 2x. Now, do we have the same thing but with a negative in front of it? Yeah, we do. So is it the same but with a negative in front of it? The answer is yes. So because we can say yes to this, we can say our function is odd. Now, both of these may fail, and in such case, we just say it is neither even nor odd. Graphing functions using stretches and compressions. So, like before, we can have stretches and compressions, and that makes our graphs skinny or wider. Horizontal stretch and compression. Given a function f of x, a new function g of x equals f of b of x, where b is constant, is a horizontal stretch or horizontal compression of the function f of x. If b is greater than 1, then the graph will be compressed by 1 over b. Compress means be made to look wider. And this is if your number is less than 1. If b is between 0 and 1, then the graph will be stretched by a factor of 1 over b. If b is less than 0, meaning negative, then there will be a combination of horizontal stretch or compression with a horizontal reflection. Okay, so this is how your graph can be made to look wider or skinnier. And here we see some pictures. So if we start off with x squared, this one right here, being our parent function, if I have 0.5 x squared, this is a number that's between 0 and 1. So that would be a horizontal, well, that's a horizontal stretch. So it kind of made to look wider. So disregard my note above. And in the smaller one, we see 2x quantity squared. That's a horizontal compression. It kind of makes it look thinner. All right, so that's it for this section. For the most part of your homework, you'll be given functions and you just identify the type of stretch compression that you'll see in your function. That's it for this section. Thank you.